Pacmania is an isometric maze game that was developed and released by Namco for arcades in 1987. As the 9th title in the Pacman video game series, it soon gained a highly positive critical reception for its uniqueness in gameplay, such that it was also ported to many home computers. I'm sure you're already familiar with the basic game mechanics of the first Pacman game, and Pacmania introduced not only cutting-edge 3D style isometric graphics, but also new features like 4 different arenas to explore, the ability for Pacman to jump, and also power-ups. So how would you code this game now in something like the Unity engine? This tutorial video will show you how to do this. Firstly, to get the basics out of the way, this tutorial will focus mainly on the programming and Unity editor parts of this game. I won't really touch on creating 2D art or audio. Also, it's assumed you have a basic understanding of C# programming, Unity, and Unity's component-based design. Also, it's worth mentioning that Pacmania isn't the simplest game you can create, but it's still relatively a very simple game in terms of what you can actually do with Unity. Saying that, this game is way too large to cover everything step by step, and it's not really possible for me to talk through every single line of code or every process. So instead, I'll just be jumping in and out of the code base, focusing on important parts of the game and showing you how I would implement them. The code for this version is written in C# and which is clearly not how the original 80s version was programmed. So here we'll be using a modern coding technique on an old style arcade game. The source code for this game is available on my GitHub page, and it will be very useful if you download this so you can use it as a reference as we go along. So in this video I'll be talking about, is Pacmania a 2D or 3D game in terms of programming? How to code Pacman and ghost character movement, collision and eating pellets, state machines and how I use them for ghost behaviour, and also how to keep track of the state of the level, game sessions and how to keep track of score and lives across different Unity scenes, 2D sprite sheet animations, ghost AI, game pickups and bonuses, playing audio, head-up display, as well as cutscenes. So let's jump straight in. Obviously you need Unity, either the latest version or the latest long-term supported version. Also I'm using Visual Studio as my code or script editor. So to start with, create a new 2D project. I know Pacmania is meant to look 3D, but in terms of graphic assets we have, they are all 2D sprites. So let's create a 2D project for now. Next you'll need to import the media files. All the media files can be found on my GitHub page. I'll provide a link below in the description. So I import the graphics, sounds, fonts and shader folders into Unity like so. To give the artwork that low resolution authentic look, I will be setting all the sprites compression to none and filter mode to point. All the sprites in this game are very small in size, so compression at this very low level can add unwanted artifacts. Also, it's worth saying that the file structure for this game is very much based on asset type rather than feature based, which is generally better for a smaller project like this. Next, I'm going to import the arena maze straight into the editor. When I drag the sprite into the scene, it makes a game object for me with a sprite renderer component. You could create this arena maze from Unity's tile maps, and this would be the way to go if you're creating a totally new game. But because the final arena sprite maze is already known and provided here, then I simply for now going to use that. Saying that, I will be using Unity's tile maps later for a 3D test scene. Next, obviously we need to add Pacman to our scene. The graphics are stored in graphics characters Pacman, but before we can do that, as the graphics for Pacman are done as a sprite sheet, we need to tell Unity this first. Set the sprite mode to multiple and then select sprite editor. In the sprite editor, select the slice to be grid by cell size, then change the pixel size to 32 by 32 and make sure the pivot is set to center. Then select slice and assuming everything was okay, select apply. You should now be able to see all the individual sprites in the sheet like so. So we drag one of the sprites onto the scene, doesn't really matter which, and again I get a new game object which I'll name as Pacman. Also for now I'll position Pacman's location to 000, also set its sprite order to a big number like 10,000. and then adjust the arena game object such that Pacman sits close to its intended start position. Actually, I'm going to change the arena sprite order. In its sprite rendering component, additional settings, set the sprite order to -1. This will be our background sprite, and any new game objects will now appear in front of it. If I select the game tab, I'll see what the game will actually look like when running. So to make this game match the original as much as possible, I'm going to change the aspect ratio to 3:4. You may need to create a new aspect type to do this. This aspect actually represents an old CRT type TV aspect, but turned on its side. Also in the project settings, select Player, then in Resolution and Presentation, untick Default is Native Resolution, and for now we're just setting this resolution to 768 by 1024, which represents a low resolution 3:4 aspect. Also, I'm going to change the camera size to 1.44, so it now looks like the original arcade. So next, we need to add basic movement for Pacman, so it can move around the arena. But before we can do this, it is important to have at least a basic plan of the game you're trying to make, else you're just coding without any destination. So when I was planning how to code this game, something that came up early on was deciding if I should code and model the Pacmania world in 3D or just 2D. So the graphics of this game are clearly 2D sprites, but done in a pseudo 3D isometric style. Also, moving Pacman up the maze isn't simply just a matter of increasing the y-axis, we also need to change it on the x-axis. Also, we need to consider that Pacman can jump. Now, we could still model all this in a 2D game, but when considering all the physics and collision this game will need later on, then things rapidly start to look complicated modelling this as a 2D game. For example, would Pacman jumping and causing its sprite to overlap a ghost sprite be considered it colliding with that ghost? Well, clearly not. There are various ways you could solve this, but the actual solution I used was to code and model the game as if it was a normal 3D game like this. The X and Y axis represents the arena coordinates across a plane, and the Z axis is used for the up direction for when Pacman jumps. However, to use the original Pacmania graphics when rendering, we really need to have a normal Unity 2D scene, and then somehow convert the 3D positions into its equivalent 2D sprite position. So in order to do this, you have to separate the object's rendering position from its conceptual position, where it actually is in the 3D world. As we know, Unity stores game object positions in a default transform component. So to make things as simple as possible when using the Unity editor, I left it as a 2D scene with the transform position representing the game object's 2D sprite location, and instead create a new variable inside a character movement script attached to the game object called arena position, which is of type vector3 to represent the conceptual 3D location. Then, in the character movement script, after each move update, I set the sprite's position to its calculated 2D position. Also, I added a flag to a script attached to the arena game object, which tells us whether or not the scene graphics are 2D or 3D. This then allowed me to create a test 3D scene of the game with placeholder 3D graphics, or instead be able to play the game as a 2D scene with isometric sprites. The only downside to this is that Unity uses this transform component for physics and collision calculations, which in our case would need to be 3D. But luckily, Pacmania is such a simple game that physics and collision wise, it is actually simpler to code the movement and collisions checks in our scripts, rather than using Unity's 3D rigid bodies and collisions, which was intended for much more complex tasks and would be a bit of an overkill for a game like Pacmania. Also, having custom movement and collision code allows us to have full control, which will come in handy when trying to replicate the original arcade game version as closely as possible. For example, did you know Pacman's jump doesn't actually follow real-life physics? Now that is all out of the way, and congratulate yourself if you understood most of that, let's start by looking at how we can create the scripts needed to deal with user input, movement of Pacman, and scrolling of the camera. Firstly, in the scripts folder, I've added some subfolders. We know there are going to be quite a few scripts to this game, and we don't want to have all the scripts in one root folder. Typically, I only want one folder to have, say, no more than 12 scripts or so. As I already know the folders I will need, I've already added some here, along with the Pacman controller script, the character movement script, and an arena script, and a scrolling camera script. Firstly, we're going to look at the Pacman controller script. This script's responsibility is to generally control the Pacman game object, and later coordinate other components needed for Pacman 2. In Pacmania, the Pacman character is always trying to move in its current direction, but the user will want to change this direction. However, it won't actually change direction until Pacman reaches a turning point in the arena. So we've actually got two separate things going on here, current direction and a desired input direction. We store the desired direction here in the Pacman controller script and pass it into a movement script here on each fixed frame update. The desired direction and jump, come to mention it, are set here in the onMovement and onJump methods. These will be called from Unity's relatively new input system. So to make sure you're using the new Unity input system, select Windows Package Manager, make sure this is set to Unity Registry, then scroll down to Input System, and you may need to install it here. If it asks, make sure you apply this new input system to your current project. In the Assets Input folder, I've created a new Unity Input Action asset. When I open it, you can see I've set up some actions here called Movement and Jump, and assigned some keys to these actions. For the cursor movement, I've set the composite type to 2D vector and importantly set the mode to digital rather than digital normalized. What this means is that it's valid to have a movement of up and right both set with 1 at the same time. Later on, the code will decide which of any of these desired movements to actually use. Then in the Pacman controller game object, I've added a player input component and assigned the actions to the input actions asset I've just showed. I also set the behaviour to invoke Unity events. Then in the events themselves, I set them to call the onMovement and onJump methods I just described. If you're not familiar with Unity's input actions, then there are plenty of tutorials online. Looking back at the fixed update method, as this script will be repeatedly referencing the movement script, for efficiency we cache a private reference to it in the await method. Also, it is common practice to add the require component attribute to the class to tell Unity that this script needs this component to work. If I hit F12 on this move method, it brings up the character movement script, so let's see what's going on here. The movement script will be responsible for moving a character around the arena and will update the position based on a current direction vector every fixed update iteration. Because the movement of all the characters of the game, i.e. Pacman and the ghosts, will be basically the same, it makes sense that all the characters make use of the same script. Here I've added some variables. Firstly, default speed, which represents the normal speed the character will move per fixed frame update, i.e. 1.4 pixels every 60th of a second. Current direction, which I talked about just now, represents the current direction the character is moving in. Because I want both these variables accessible in the Unity editor, I've added this serialized field attribute to them. By default in Unity, it will make any public variable accessible in the editor. But in object-oriented programming, like C#, you generally want to keep variables private if they are private to that class. So it's better practice to make them private and then add this Unity attribute to them, which still makes them accessible from the Unity editor. Because I need to get read access to these variables outside this class later on, I've added some getter properties here too. I've also added the arena position vector 3 variable I talked about earlier, which will represent the conceptual position of the character in 3D. In the move method, we simply check to see if a desired direction is different to our current direction. If so, it changes the current direction to the desired direction. Note that this code will only allow us to move up, down, left or right individually and not multiple directions like diagonally. We then add to our arena position vector our current direction vector multiplied by the default speed. Finally, the transform calculation to convert our 3D arena position into a 2D Unity sprite screen position is done here by calling this method on this arena script. We can look at this method in this arena script. I won't go into details about this calculation, but in short, it adjusts the x-axis position based on the y-axis. i.e. as you move up and down, it also affects the x-axis. This y-scale value here is based on the fact that in Pacmania 3D world, the tiles will be at one aspect, but the 2D artwork that represents it has a different aspect. So I had to add this scaling to adjust for this. In short, without this, Pacman would have to travel at a different speed on the y-axis compared to the x-axis, which doesn't really make sense. It's reasonable to assume that Pacman was supposed to be travelling at the same speed no matter which direction it was travelling in. Also here you can see the isometric flag, which can be set in the editor, and by the default is set to true. But if this was a 3D level, not a 2D isometric one, you could turn this off, which means calling this method would simply return the same input vector. Briefly, going back to the Pacman controller script, I didn't mention why we call the move method in Unity's fixed update method rather than just the update method. If you don't know what the difference between the two Unity's update and fixed update methods are, then there are good tutorials online. But to summarise, update is called every render frame on a game object, which will vary, and fixed update is called at a predetermined fixed rate, and typically will be lower than the update rate, but actually can be much higher for mobile devices, which will often render at 30 frames per second. For physics and collision, use fixed update, as it makes it so much easier to design and code. In fact, a lot of the scripts in this game will rely more on the fixed update method. This is because the original arcade game code ran at a fixed rate of around 60 frames per second, so this helps us a lot when trying to replicate things. Now saying this, I need to change the default Unity's fixed update rate frequency from the default of 50 frames per second to 60 frames per second. Go to Project Settings, then Time, and set Fixed Time Step to 0.01666, which represents 1/60th of a second. If I hit play now, you can see I can move the Pacman up, down, left and right, which generally moves how you expect this for an isometric view. However, we also want the camera to follow Pacman around as well. So one really simple solution to this is to make our main camera a child game object of Pacman. If I run this now, it works, and always keeps Pacman at the centre of the screen. The problem is that for our final game, when Pacman jumps, we need the camera not to follow this jump as well. So I'm undoing this, and instead we're going to use a scrolling camera script I've created and attached to our camera game object. In this script, I simply cache a reference to Pacman's character movement, and on each update method I simply adjust the camera position based on Pacman's position, but also taking into account that I need to clear Pacman's arena position Z value. This Z value will be used when Pacman jumps. If I run the game now, everything works just the same as it did just now. Okay, something we need to consider early on is that our code is sooner or later going to need to know about the arena maze structure in terms of walls and passageways. For example, when doing ghost pathfinding, we could place game objects down in the Unity editor to try and cater for this, which may be a hierarchical structure of some kind or node system. But to be blunt, this is overly complicated for what we need in a simple Pacman type game. And also, it is typical for a game code to store some kind of simplified internal map of the environment for it to assist with navigation and object reference queries. For Pacmania, the simplest type of map we can use to store the arena maze structure is a 2D array. So here we store a 2D array of integers, where each number represents something in the arena. The array here represents the Blocktown arena maze, and we store 0 as an empty space, 1 as a pellet, 2 as a power pellet, and 4 as a wall. I use numbers here simply because I made this array by hand in the code editor, but in a more complicated game, you could have a more elaborate map with it being code generated from, say, Unity's tile maps, or from some third-party tool. So each element in this 2D array represents a single tile in the arena. In the arena script, I've added some methods to calculate which tile a given character is located at. A character's current tile is calculated as the tile which it mostly occupies at any one moment, as it can obviously overlap across two tiles. Also, I've added some methods to work out an arena position based on a tile, which would be the tile's center position. Now in the character movement script, I've made sure we can only change our current direction if the character is located at, or very close to, the center of a tile, and the passed in desired direction vector is heading towards a tile that it is allowed to be in. For now, this means a tile that exists in the array and is not a wall tile. The one exception to this is that we don't need to be in the center of a tile to turn around 180 degrees. So I've added code here to handle this case. In Pacmania, you can turn around as quickly as you like. Because we have this simplified internal map of the arena maze, we can also make use of it for wall collision and pathway tests. For this, each character is basically considered the same size as a tile square. After we have applied the movement to the character's arena position, we do a check here to see if we're not starting to move into a wall. The collision check for a wall hit is very simple now we have our internal map, and boils down to getting the character's arena position, adding half a tile length along its current direction, which then gives us a test point. We then check if this test point is considered to be in a wall or not. If it is, we move the character back to the center of its current tile. If I test the game now, you can see we have wall collision working, and I can now travel around the arena maze as expected. Currently, Pacman does not appear behind walls that we would expect it to be hidden by in the final version. I'll show you how to fix this later on. In Pacmania, Pacman can eat or pick up various items. This includes pellets, power pellets, fruit and special bonuses. To create all these pellet game objects just in the Unity editor itself would soon become tedious and prone to errors. So because we already have an internal map of the arena with ones representing a pellet, I simply create them all in the arena start method using Unity's instantiate method. Now for our arena script to generate these game objects on the start method, we need to store some public variables of the pellet and power pellets as prefabs that we can then use. But before we do this, I know that these pickup type game objects are going to need their own scripts. I've outlined here in this class diagram how Pacmania pickups work, with all the pickups inheriting from this base pickup class. If this was a bigger game and there were other types of things the user could pick up, then this would be a classic place you could add some kind of interface, with the onPickedUp method being defined as its interface contract. But as Pacmania game logic is already fully known, I left the pickup class as a base abstract class and also added some common shared functionality to the base class in terms of adding a score. I've also already added the scripts for some of these pickups to the project here. So back in the editor, I'm going to make some prefabs for these items. First, I'll drag a pellet sprite into the scene to make a game object, and then drag this game object into the prefabs pickup folder I've created here to make it into a prefab. For the pellet prefab game object, I've added the pellet script component. I did the same for power pellet prefab, but used the power pellet script and sprite instead. I can then remove the pellet and power pellet game object from the scene and then drag the prefabs I just made onto my arena script. So each time I play the game now, the start method gets called on the arena script, which then instantiates all the pellets in exactly the right location. Also in the arena script, I've created an internal 2D array which references the pickups object stored in each tile. For Pacmania, only one pickup can ever exist for any given tile. Also, I can modify this array at runtime to keep track of game objects Pacman has actually picked up. We can do this by calling this method and passing null as the pickup type. Next, I've created a Pacman collision component to Pacman's game object. The responsibility of this script is to check if we have collided with another game object like a pickup or later on a ghost. I've added this check collision method here, which then checks if we have touched a pickup. It's worth noting that this can only happen if they are both located on the same tile. As you can see, the actual collision check comes down to one line of code, which simply checks the distance between a game object and Pacman. This is essentially a sphere-to-sphere collision check. Also calling magnitude squared is considered good practice instead of just calling magnitude because it is vastly more efficient and does not use an unnecessarily square root call, i.e. we simply pre-square the sphere radius on startup. I found 8 pixels seemed to be a good value that matched the original arcade game. As you can see here, when we touch a pickup, it destroys it, removes it from the arena map, and then calls the onPickedUp method for the pickup object. Running the game again, we can see Pacman eats up all the pellets as it wanders around the arena. Before we get started with ghosts, I wanted to talk about this level game object, a level script I've added to our scene. This type of object is useful in game coding because it can be used as a holding object for referencing top most important scene objects. For example, if some kind of character script needs to access the scene's audio manager and the ghost manager and the arena, for example, then the script may need to hold a reference to all these different game objects. But because we've introduced a level script which references all the important game objects, then the script only actually needs to have a reference to this level script. This can massively cut down on things like Unity's find object type of calls, which can be very inefficient. Also, the level itself can be considered to be in different states, like get ready, pause or game over, so it would also need to handle that, but I'll talk more about that later. So, in this game, Pacman is hunted by ghosts, which also wander around the arena. If Pacman touches a ghost, it gets killed, but if Pacman eats a power pellet, then the hunted becomes the hunter, and for a brief period ghosts become frightened, and Pacman can get his revenge by eating them if he manages to catch them. If a ghost gets eaten, then all that remains of the ghost is some kind of spiritual eyes, which then quickly return to the ghost's nest to get regenerated into a new ghost. This deadly, then frightened, then eaten, then regenerated behaviour for the ghost can be represented in this state diagram. Also, when ghosts are in a deadly state, then they also do a different number of additional sub-behaviours. This is scattering, where a ghost generally tries to hang around its preferred area of the arena, and also a chasing behaviour, where the ghost is chasing after Pacman. So for these sub-behaviours, or states, we can add these to our state diagram. I've also added something called confused state. If Pacman manages to successfully jump over or close to a ghost, such that the ghost looks up, then it becomes temporarily confused and will travel around the arena in a random way for a short period. So, when coding the logic for all these ghost behaviours, it also makes sense to separate each behaviour into its own class. This can be done in code by using something called the state pattern. So for our Pacman game, I've added some scripts here which is an implementation of the state pattern. Firstly, a state machine class, which represents the complete state machine itself and contains a list of all the states a game object can be in. Also, I've added an abstract base state class which any state class would have to inherit from. Note that these classes are not mono behaviours, but instead will typically be used by the game objects within our game. Here I've added all the ghost states classes in this subfolder, and also created a ghost controller script which will work similar to our Pacman controller script, but instead will be a component of a ghost game object. In this script we set up and create the state machine in the start method. For simplicity, the state machine's initial state is the first state in the states list, which in our case is the scatter state. Also in the script, I've added a desired direction variable in the ghost controller similar to the Pacman controller, and also a target tile variable which represents the tile the ghost wants to travel to. In the fixed update method, as well as calling the character movement move method, I also call the update method on the state machine. If I go into the update method itself, it simply then calls update on the current state with a return type representing the state machine should change into. If this is to remain in the current state, then it simply returns its current state type. If I briefly look at the code inside scatter state, you can see that in its update method that it sets the ghost controller's target tile to the result of calling the Ghost AI component's getScatterTile method. Also, it checks here if it needs to switch into the chase state and also calls update method on its parent deadly state. The deadly state update method then does functionality that is common to all deadly substates, in that it does checks to see if it needs to go into a confused state. Looking at the chase code, it is very similar to the scatter, except it calls the AI getChaseTile method instead. So in our game, there is also a game object called Ghost Management. This will contain components for managing the ghosts. And for now, I'm going to add the scatter chase timer component to it, which responsibility is to alternate between scatter and chase state after some user defined time. Here you can see I've added some periods where the user can define the amount of time a ghost should spend in scatter and chase state. The first period is 10 seconds for scatter, then 15 seconds for chase, and on the next period is scatter for 8 seconds and then chases for 15. The last period is then repeated, but you could add more periods here if you wanted to. So this game object is then used by all the ghosts to keep track of which state they are supposed to be in. As you can see, the ghosts should either all be in chasing together or scattering together. So for each ghost in Pacmania, which have their own names, Blinky, Inky, Pinky, Clyde, Sue, Spunky and Funky, they all work together as a team, with each ghost having a slightly different role. For Blinky and Sue, this is directly chasing after Pacman, but for other ghosts like Pinky and Inky, they will try to cut off Pacman's escape routes. So I've just placed these ghosts anywhere on the scene because in the start method they will move to their predetermined nest tile. I've added some ghost AI type classes that all inherit from a ghost AI mono behaviour. In the editor itself, I can simply add any desired AI component I like to the ghost game object, but obviously a game object with Pinky's sprite would want Pinky's AI, but it doesn't have to be like this. Inside Pinky's AI class, you can see that the getScatterTile method, which got called from the state code, simply returns the top leftmost tile of the arena, and for the getChaseTile method, it simply returns a tile 4 tiles in front of Pacman, trying to anticipate where Pacman is heading. Going back to the ghost controller script, we have this variable called targetTile, which represents which tile the ghost is currently trying to travel towards. Pacmania's ghost pathfinding is actually quite simple. When a ghost reaches the centre of its current tile, it finds all possible directions it can travel in by using the internal map we defined earlier. Ghosts do not turn around in this situation, but do so when a state change occurs, like going from scatter to chase, or later when it becomes frightened. So then the script calls getShortestPath method, which loops through all these candidate tiles, finding the tile which travelling towards would be the closest to the target tile. This simple pathfinding algorithm actually works surprisingly well in this game, and is universally used when chasing, scattering, or simply wanting to return back to the ghost nest. Back in the Unity editor, I make sure that all my new ghosts have a character movement component, a ghost controller component, and a ghost AI component. Then when I hit play, you can see that all the ghosts now wander around the arena as expected. Typically when we write AI or state control type classes, it would be nice to know what state a ghost is actually in. So you could access from Unity's debug inspection window. But for things like this, it is much nicer and clearer to add some debug type gizmos strings, which can be viewed in the scene window, which you can see here. In the ghost controller script, you can see I've added a Unity onDrawGizmos method, which draws text as the ghost position, telling us its current state as well as drawing a line to its current target tile. When you have useful debug information like this, it makes debugging and testing so much easier. Just to quickly mention that if you are finding this video useful, then let Google know by hitting the like button below. This tells Google that other people like yourself would also be interested in this video. Animations are done by using Unity's animator controller. In the editor, make sure the animation window is present or open it by selecting it in the Windows tab at the top. Now when I select the Pacman's game object, I can select Create in the animation window. Then create an animation file called Pacman left. Here you can see I've already created a subfolder to store this in. Once you've created this animation, Unity will automatically also add it to the animator component to the game object and assign it a controller. So from here I drag and drop Pacman's 5 left animation sprites. Because Pacman animation has his mouth opening and then closing, I actually need to complete this full cycle by adding 3 more sprites, but in the reverse order. So we end up with sprites 1, 2, 3, 4, 5 and then 4, 3, 2. Because the animation loops, it will then automatically start again with sprite 1. I then set the samples to 30, which tells the animation that it needs to do playback at 30 animation frames per second. If I hit preview play here, you can test the animation. To do other animations, I can select this drop down and select create new clip, and then repeat this process for Pacman's up, right, down animations. After we've done this, we need a way to control these animations. This is done in Unity's animator window, which can be brought up by double clicking on the Pacman controller. If you're not familiar with this window, then basically it's a state machine where each state represents a different animation. So what we need to do is add parameters which tell Unity which animation state to be in. Here I've added some float types, horizontal and vertical parameters, which will represent and eventually map to our current direction variable inside our character movement script. Because Pacmania sprites animations are very simple, 2D sprite based, we can simply snap instantly from one animation to another based on these parameters. I could add transitions from all states to all other states based on these parameters, but Unity has a useful state called anyState, where I only need to create one transition to also represent this. I right click on it and select Make Transition. I then drag the arrow and click on our left animation. So for this transition, I need to add a condition which would be our horizontal is less than 0. Also in the settings, turn off fixed duration, set this to 0 and also untick can transition to self. You can also preview this if you wish. I have now added all the other transitions for Pacman. Now to set the transition parameters from a script, I've added this set animation and sprite order method to our character movement script. In this method, we get our animator character component, which I pre-cached in a wake method, and then set the horizontal and vertical parameter string names to our current direction. I had to reverse the Y value because negative Y for us is actually travelling up the screen. So in our move method, we simply call this set animation and sprite order method. When I run the game now, hopefully Pacman will now have its animations. I repeated this process for all the ghosts, except the ghosts are a little bit more complicated than just 4 animation types. Because ghosts can also be in different states like frightened and eaten, these all need their own sprite animations. I added some Unity substates to our animation controller and also added an additional parameter called state. If I double click on the frightened substate to go into it, you can see it is very much the same as for Pacman's animation controller, except on each transition condition I had to make sure the state parameter was set to some value which was unique for this substate. For Ghost, an animation state of 0 represents normal or deadly, 1 represents frightened, 2 represents eaten, and so on. Back in the code, I actually made these numbers into an enum for readability, and inside the Ghost states we wrote earlier, I set the animation state where appropriate. When I run the game now, the ghosts also have animations. As we saw just now, we also need to set the sprite draw order on all our characters, so it's worth talking about that now. Sprite ordering is a big problem in isometric type games. As I play the game here, you can see Pacman is in front of blocks it should be partially hidden by. The solution is twofold. Firstly, if you look in the Graphics Arena's Blockdown folder, you can see I made duplicates of some of the background sprites here with transparency set on the pixels which weren't part of the block itself. I then drag these sprites onto the scene, making new game objects, and place them over their equivalent background part. I also made sure these new game objects were child game objects of Blocktown. The second part was to then set in these new game objects the sprite component's additional settings order in layer to some predetermined number ranging from 0 to around 1000. Then, as you saw earlier, I also set the character's sprite order in layer as the character moves. Sprites with bigger order numbers are simply shown in front of sprites with lesser order numbers. In short, I consider each tile to be a different number, and based on what tile the character is in, I set the sprite order number accordingly. By using this, I managed to solve this sprite ordering problem. I've also added shadows to our characters. These are simply subgame objects, which means they share position with their parent game object, and simply draw a shadow sprite. There is also a shadow script component added to them to deal with jumping. In the code, I've added power pellet functionality so we can test out the ghost, frighten, eaten, and regenerate states. In the power pellet on picked up method, I now call frighten all method on the ghost manager. The ghost manager is now a component of the ghost management game object and holds a reference to all the ghosts in the current level. The frighten all method then simply calls fright on all the ghosts, which then in turn sets the current ghost state to the frightened state. In the frightened state on state enter method, it sets the animation to the frightened animations. Also here, we change the character movement speed as ghosts move slower in a frightened state. The frightened state update method will then set the ghost target tile to a random and also go back to the scatter state after a period of time. If, however, going back into the Pacman collision code, Pacman touches a ghost, then it calls the eaten method on the ghost, which then changes the ghost state to the eaten state. Just briefly, you can see that if the ghost is not frightened but deadly, then Pacman should actually die. In the ghost eaten state code, on the on state enter method, we change the animations again to eyes, change the ghost movement speed to fast, and also set the target tile to the nest entrance. In the update method, once the ghost reaches the nest entrance, it sets the target tile to inside the nest, and once it is inside the nest, it changes its state to regenerate state. The regenerate code simply stops the ghost from moving here, starts off the regenerating animation, and then, when the animation completes, it goes back to a scatter or chasing state. When I play the game now, I can test all this game logic out here. Eat power pill, eat ghost, the ghost goes back to its nest, regenerates, and starts out again as a new ghost. The final thing I want to talk about in this section is jumping. In Pacmania, Pacman and some ghosts have jumping ability. In the Pacman game object, I've added two new components, jumping, which gives a character jumping ability, and also a jumping degrader. For Pacman, after the level has been running for a few minutes, it starts to slowly lose the ability to jump as high as it used to, so this component handles that degradation. To enable a jump, in the Pacman controller script, if the user hits the jump button, we then call jump on the jumping component. In this jump method, we set a flag to tell the script it is jumping. Then in the update jumping method, which gets called from our character movement script, it sets the arena position Z to follow the next value along this table of jumping height values. Pacman's jump doesn't follow any real world physics or algorithm, so I had to reverse engineer this from the arcade game to work out these numbers. This script also handles bouncing and re-jumping, but I won't go into that. However, I will mention that I added an event in this class called jump. Events in C# work the same as the observer pattern, in that this event holds a list of observers who get notified whenever a jump occurs. This can be perfectly demonstrated here when we look at the jump when Pacman jumps component, which I've added to Funky's game object. As well as the jumping component, Funky and Spunky are both jumping ghosts in Pacmania, but as you can see their jumping power is less than that of Pacman's. In the jump when Pacman jumps script, you can see in the start method I simply subscribe to Pacman's jumping component jumped event. When Pacman jumps, it will invoke the observer subscribe methods, i.e. Pacman jumped, and here you can see it then calls jump on Funky's jumping component. The net result of all of this is that when we play the game, I can make Pacman jump by hitting the jump button, but also Funky is mirroring my jumping as well. I want to talk about some things here that are important in game development, but quite often overlooked, mostly because they come later in the project and not really thought about when you start making a game. That is, level state, game sessions, and also audio. As mentioned earlier, the level itself can be considered to be in different states, like get ready, Pacman dying, or game over, so the level needs to behave differently depending on which state it is in. This state diagram shows all the different states the arcade version of Pacmania can be in, so when the level starts, or after Pacman has died, it goes into the get ready state, where the game pauses for a while. After this, it is considered to be in the playing state. If Pacman eats a ghost or a bonus, then the score rises up and also briefly pauses the game, which I call the eat and paused state, before going back to the playing state. If Pacman gets killed, then Pacman spins, and if Pacman loses all his lives, it does a game over sequence. If Pacman collects all the pellets, it does a win sequence before proceeding to the next level. So to code this, I've added a new state machine in our level script, and also add the level states code in their own subfolder. If we take a look at the dying state, which the level will change if Pacman touches a deadly ghost, then in the onStateEnter method it pauses all the characters, greys out the background by using this grey out sprite component I've created and attached to our arena game object, and then should fade out the music. Then in the update method, after a short period it starts the spin animation on Pacman, which also disables the background grey effect and hides all the ghosts. Then later it calls the doPacmanDied method. In this method we decrease the number of lives in the game session object, which I'll talk about next, and if Pacman still has lives, it restarts the level here and then goes on to the get ready state. However, if the game session has no lives left, it changes to the game over state. Some of you may be asking why I did not use coroutines instead of frame counting in the update method. That is also a valid way of doing it. In fact, I use coroutines in many places in Pacmania, but to help me replicate the original game, I found it easier to code it like this. As I just mentioned about game sessions, I'll talk about it now. For Pacmania, we need to store at a global level the concept of some kind of game session which is persistent over many levels or scenes. It will keep track of our score and lives, and also handle things like what scene to load next depending on what happened in the level. For example, start a new level, finish the game, go to the high score table, or back to the main menu, and also initiate the playing of an intro cutscene which exists in Pacmania. In the scripts folder, we have some new code in a game management subfolder, like game, game session, player game session, and demo game session. The player game session code handles the things I just described, but because the player can be playing the game, or instead the game could be running as a demo session, also known as a tracked mode, where the computer is playing by itself, I needed to separate this game logic. Both game session classes both inherit from an abstract game session class. In the game session parent class, I store things like lives and current level number, as well as the score. And in the player game session, you see I have implemented the abstract start next scene method, which works out what scene should happen next, as well as if we should show some intro or cutscene. But in demo game session implementation of this, it simply runs for a sequence of predetermined scenes, like a particular level number and high score table, for example. In the game, we are always considered to be running in either one of these two types of game sessions. Either the player is playing the game, or the game itself is running things by iterating between demo level scenes and menu script scenes. Now, because this game session object needs to be persistent between scenes, it actually makes sense to store the game session in a singleton class. I've added a singleton class here simply called game, which does this and follows the singleton pattern by only allowing one instance of this class. This game object's responsibility is to simply hold onto the current game session, which will be the player one or the demo one. I've coded Pacmania as a single player game, but as you can see, if this was ever to have a two-player ability like the arcade, you could add a player 2 game session to the game class here as well. The arcade two-player mode isn't actually two people playing at the same time, but instead is turn-based and switches between players each time one dies, which I didn't think was worth implemented for our version. A quick note about singletons, which I won't get bogged down discussing now, but in software engineering in general, they are often not the best solution to problems, and in general you want to limit the use of them. Because the way Unity works with creating and destroying all the game objects between scenes, you are kind of forced into using singletons as a solution to persistent data. And I think having a global game object which represents the whole game is fine. I have seen some games use singletons implemented as mono behaviours type classes. Whilst I'm not totally against that, I would personally generally avoid it and stick to a pure implementation of the singleton pattern. Finally in this section I'm going to talk about audio. Playing audio in Unity is actually quite simple, and typically you can add an audio source component with an audio clip assigned and then call play on that component. That way is fine, but when a game object has multiple sounds it can easily become a bit cumbersome and bloated. So a better way is to add some kind of manager object that handles all the scene sounds for you. In our project I've added an audio manager script which I've added to an audio manager game object in our scene. The responsibility of this script is to hold a list of all the audio sources the level may need. In the script I hold onto a list of instances of sound class which I've also added to the project. The sound class itself stores a sound type or name of the sound which can be used to uniquely identify the sound within our game, for example eat power pellet. Also it stores the audio clip itself and also whether or not the sound clip should loop. Then back in the editor I can create a list of these sounds and populate it with the sounds I need for that level. Now in our code we can simply make a sound play by calling play on the audio manager with a sound type. I've also added some helper methods in the audio manager to have stop and fade out type functionality as well. If you look at the fade out method you can see it creates a Unity coroutine which in turn slowly decreases the volume over a period of time. It's worth noting, if you're not familiar with Unity coroutines, that they have nothing to do with threads, which an experienced programmer may think they are. I know I did when I first came across them. So don't think you're getting into some kind of multi-threaded hell if you use them. Okay, next I'm going to talk about bonus pickups. In Pacmania there are various fruits and special bonuses that appear in a tile close to the centre. In our game I achieved this by adding a game object to the level scene with a script called bonus spawner. This script's responsibility is to spawn up to 3 predefined bonus prefabs after a number of pellets have been eaten. There is also a secret bonus that appears randomly. The script itself subscribes to the eaten pellet event on Pacman's collision script, which then gets invoked each time Pacman eats a pellet. This then calls this bonus spawner eaten pellet method, and once a certain number of pellets have been eaten, the method then spawns the bonus at the bonus tile location. If I look at the bonus prefabs, like the fruit ones, you can see they are simply made up of a sprite component and the fruit script component. The fruit script is a child class of the bonus class, which in turn is a child of the pickup class I talked about earlier. So on its overridden onPickedUp method, as well as calling the parent method which increases the score, it also makes the eat fruit sound and also calls the level score spawner spawn method. The score spawner is another game object in the scene and has the responsibility to spawn a score sprite at a given location. It does this with these prefabs I've already created and assigned to the score spawner script. Each of the score's prefabs have an animation which I've created here with Unity's animation and play when the object gets instantiated. Going back to the score spawner script, you can see here that it invokes any subscribers to this spawned event. It so happens that if I look at the level script, that it indeed subscribes to this event, and when it gets called back, it sets the level state to an eaten pause state. For Pacmania, whenever a score is spawned, it also always pauses the game for a while. While we're in this level script, you can see it also subscribes to these two other events, when Pacman eats a pellet and also when Pacman is dying. When a pellet is eaten, the level checks if all the pellets have been eaten, and if they have, then it changes the state to a winning state. Similar, when Pacman is dying, it changes state to this dying state which I talked about earlier. The other bonus types in Pacmania include a green pellet. When I look at the onPicked method, it simply increases Pacman's speed. This speed increase remains until Pacman gets reset, which will either be after it dies or when the level ends. Also, there is a red pellet bonus, which simply is another power pellet, except it sets the Ghost Manager's red pellet eaten flag to true. Basically, when we look at this code, the Ghost Manager will score a ghost eaten event slightly differently, as in you get a lot more points when eating a ghost after eating a red pellet. Now we've got the basics going for our level scene, the next thing we want to do is create new levels for the game. It makes sense for each level in Pacmania to be in its own Unity scene. When creating additional scenes, the first step is to identify all the common or default game objects in the level we currently made and then make them into some prefabs so we can use them in other levels. This can be done by dragging the game objects into the prefabs default folder which I made earlier. Other levels will need a different child arena script, different ghost combinations, altered ghost settings, and also different pickups. Another thing worth mentioning is that some levels use the same arena graphics but have a different colour palette. Back in the 1980s, this type of effect was quite simple because typically the sprites would be stored in a low-bit logical colour, but when rendered it would have some kind of table defined which mapped this logical colour to some actual physical colour. So you change colours by simply modifying this table. Today, with 32-bit graphics and GPUs, this type of trick can't so easily be done. For our game, I managed to achieve the same effect by creating my own palette swap component and attaching it to the arena game object. The code behind this script goes through all the pixels in the arena sprites and then swaps them based on two input palettes I have assigned. The first palette represents the colours used on the default arena, and the second palette represents what I should swap these colours to. For example, when iterating through all a sprite's pixels, if it finds a pixel colour that is in the first palette, it then simply changes this pixel colour with the equivalent colour on the second palette. Doing this made it work great, with the only small downside that it can be a little bit slow when it does this process on the scene startup. It's also worth mentioning, for this effect to work, we also need to set this read-write flag in for the sprite and also for the palettes. This is because we need to read and write to the sprite texture now. Another challenge I faced when trying to match the original arcade game was the concept of the screen wrapping around and around, i.e. on the sandbox level you can go left and keep going left because the arena just wraps around indefinitely. The solution to this problem was to add some kind of teleport game objects to our scene, a left one and a right one. The responsibility of the teleport game object script is to see if a position X value is beyond a present number, and if so, return the equivalent position on the other side of the arena. In our character movement scripts, we call this method on the scene's teleporters to see if we need to teleport. Another problem was the fact that ghosts also need to change their position based on where Pacman is. For example, if you look at the scene, then two exact same parts of the arena sort of exist at the same time, so depending on where Pacman is affects whether ghosts need to be rendered. All this was done by adding an arena wrapper component to my arena game object. On the update method for a ghost controller, it does an additional check to work out if the calculated transform position done in our fixed update method actually needs altering. Pacmania has a very basic UI or user interface. In game itself, I call this the HUD or head-up display and created a HUD game object. There are a lot of tutorials online covering Unity's user interface, so I won't go into too much detail here. What I will mention is that I created a normal canvas component on the HUD object and then created all the text objects the UI will ever need to render in game. Then in the HUD game object I added a script component called HUD, which when looking at the code allows other parts of the code to turn on and off these text objects. This includes text like get ready or game over, for example. It's worth noting that these text objects use the standard Unity's text component. Normally for a more complicated project I would use something like Text Mesh Pro, but because this game used a very basic bitmap font, which I created and can be found in the fonts folder and is called Pacfont, I found it was actually easier in this rare particular case to use the default Unity text component. Also, something else worth mentioning is that the canvas object itself has its render mode set to screen space camera, with the canvas scaler set to scale with screen size. The reason I did this was because Pacmania needs to always run in a 3x4 aspect, no matter what the display aspect is. So for something like mobile support, you still need to have the game running in 3x4 aspect, and thus needs to have black letter boxes or pillar boxes when the display is at a different aspect. By default, Unity doesn't force the game to run at a given aspect on a mobile, so the solution also involved adding this letter boxer component on my main camera prefab. The responsibility of this script was to make sure the camera render rectangle is always 3x4 aspect, and if necessary, to render out the black bars. Outside the game itself, we have various scenes which need to exist. I either store them in this menus folder or a cutscenes folder. The startup logo screen, world select and other menu type scenes are here. These menu scenes themselves are pretty simple and mostly just display text and images on a UI canvas, but I like to talk a little bit how I created some of the level intro cutscenes. So back in the editor I'll open one of the simple cutscenes like the Blocktown intro. If I hit play you can see that the cutscene simply has Pacman jumping across the screen from left to right with the ghost chasing, and the ghost looking up each time Pacman jumps. So to create this, the first thing I did was to add some background sprites and some canvas UI text such that it looked like this. Then I added the Pacman prefab to the scene and also some ghost prefabs. Also, I've added a scene director game object and script, which responsibility is to direct the scene. If I quickly look at the script, you'll see that all it actually does is wait for 4 seconds and then tells the game session to start the next scene. The script also changes the ghost animations so they look up when Pacman is jumping. Now, this script could also do the code for making Pacman move and jump and making all the ghosts chase Pacman, but I didn't do it like that. Instead, what I did was make use of Unity's Game Object Recorder class. What this does is allow us to record a movement which occurs whilst playing the game, and then save out this movement to a Unity animation clip, which we can then use later on. So I've added to our project this record animation script, which if I look at basically does this in-game recording. In the editor, if I go back to some normal level scene and temporarily attach the record animation component to say Pacman, and also assign this field to this blank animation clip I've made, then if I hit play and make Pacman jump and stop the game, you'll see that the animation clip I just made has now been populated with Pacman's jump movement. If I select Curves tab here, you can see how the X red and Z green axis should change over time for this animation. I then tidied up this animation so we can use it on our Blocktown intro sequence. Now the Pacman prefab itself already has its animations defined, so you don't want to assign this new animation to that prefab as such. Instead, a nice trick is to create some kind of parent game object, i.e. Pacman movement, and assign to this game object this new animation with an animator component. Now, because we've made Pacman a child game object of this in the scene, then when we play the scene, Pacman's screen position basically follows its parent game object, and hence we get the animation we want. I then created another animation for our ghosts as well, and note how all the ghosts are child game objects of this shared parent object, which has the animation I created. So Pacman and the ghost game objects themselves don't really do anything and by default have paused movement, but instead they move only because of their parent movement game objects I've created with these animation clips. I then repeated this process for all the other cutscenes in Pacman like so. So now we have all the scenes we need for our game. So this logo scene here I have in this menus folder will be our start scene. If I look at the build settings, you can see I have all the scenes I need for the game here, and I've set the first scene to this logo scene, so this will be the first scene Unity will run on game startup. This scene has a running script in it called logo menu, and if I look at this script, you can see the first thing it does in the start method is to create a demo game session object if one is not already created. As we talked about earlier, this demo scene will then control what scenes are now run in the demo or track type mode. If the user pushes the bounce button, then it calls this start player game method on our demo game session. This method then creates a new player game session at the global game object level and then loads the world select screen. This world select screen simply allows the player to select which level they like to start on, and then the game plays until game over. So this game can now be built for Windows and also Android, as the GitHub version contains swipe actions as well. So here we have the complete Pacmania game made in Unity. Pacmania is a classic game from the 1980s and in many ways was a worthy sequel to the original. I remember playing the game at the arcade, but I also had it on my home computer, which was an Acorn Archimedes at that time, and loved playing it. This video hopefully shows the power and flexibility of something like the Unity engine can easily be used to help recreate an old school arcade game. Pacmania is an isometric sprite based game, but I've shown here how we can set up Unity to handle this 2D rendering, but also allow us to model and code the game as if it was a 3D game. In fact, I'm sure it would not take much effort to develop your own 3D models and make this a true 3D version of this game. This video has shown how we can create movement scripts that can be shared between all the characters in the game. We've seen how creating an internal map of the arena maze can be useful for many things like pellet game object instantiation at startup, collision and pathfinding. How we can use something like the state pattern to handle different behaviours of our NPCs and also use this pattern to help us code different level states. We've learnt the basics of Unity's animation system and used it to do all our character animations, as well as create new animation clips for our Rise and Score sprites and also how we can use them in cutscenes. Also, we've learnt how to create game session objects that store player information and are persistent between Unity scenes, and how we can use the singleton pattern to store a global game object which can hold onto these game sessions. I hope this tutorial video was of use to you and gives you an idea of how you can create an old 80s classic game in the Unity engine. But also a lot of what is shown here in this video can be used in any modern game. If this video was of use, then let Google know by hitting the like button, as this tells the all-knowing Google that other viewers like yourself would also find this video useful. Bye bye.